In this video, we're going to look at the speed of waves, the energy transported by wave, and some wave reflections. So to begin, we have a wave equation, and in this one-dimensional linear wave equation, we had the speed c over the wave. But to actually find c, you need to do some physics. Now, I'm not going to do that physics for you right now, but I'm going to tell you what the speed of some different sorts of waves are. So for a thin wire, or a string, you can imagine a guitar string, or a slinky, we have some sort of transverse wave motion here. The displacement from equilibrium is given by y as a function of x and t. The one-dimensional linear wave equation for y is given by this equation here, and this term here is sitting where c squared would normally be. In this case, c squared is given by the tension divided by the mass per unit length, and so the speed is a square root of this term here. For sound waves, we have pressure, p, as a function of x and t following a one-dimensional linear wave equation. The wave motion in this case, as you can see, is longitudinal. C squared is given by this term here, and when we look at what those different things are, we have gamma as the ratio of heat capacities at constant pressure and constant volume, which is 1.4, R is the gas constant, M is the molar mass, and T is the temperature. At room temperature 300 Kelvin, we find for air a speed of sound of about 350 meters per second, which is also what we observe. Another kind of wave is the electromagnetic wave. It's a bit more complicated. There are transverse magnetic and electric components. If we look at the one-dimensional linear wave equation for the electric field, E is a function of x and t, we get this wave equation here. C squared is given by 1 divided by mu naught epsilon naught. And plugging these values in, we get the speed to be this, which is in fact the speed of light. The final kind of wave that I'll mention is a water wave. Now it's pretty complicated. The motion of the particles in water I've shown in this animation. On the bottom of the ocean, they're just going backwards and forwards because you can't go through the solid floor. And as you tend towards the surface, the motion of the particles becomes circular. But this collective motion gives rise to a traveling transverse wave on the surface of the ocean. The speed of this transverse wave is given by the square root of g divided by k, multiplied by the hyperbolic tan, that's tanh, of k times h. G is acceleration due to gravity, h is the depth of the water, and k is the wave vector. So that is, for a sinusoidal wave, that's 2 pi divided by lambda. So if we're dealing with a single frequency wave that has a particular wavelength and frequency, then we can write down the speed of the wave. But if we have some sort of mixture of two different waves with different wavelengths, then they'll travel at different speeds. And this is an example of dispersion, and water waves are strongly dispersive. This is in contrast to, say, light in a vacuum, which is not dispersive at all. Light can undergo dispersion if it travels into a medium like glass, where the speed changes as a function of wavelength. Sound waves in air are very weakly dispersive. It's hard to measure any sort of dispersion for sound in air. And transverse waves propagating along a thin wire tend not to be dispersive. Although if the wire becomes stiff, then you can start to see dispersion. The energy transported by wave per second, i.e. the power, so it's proportional to the square of the amplitude. For example, on a string, the power transported is a half. This is the linear density, the square of the angular frequency, and A is the amplitude and C is the speed. So it's proportional to the square of this amplitude here. For sound, now we have power per meter squared, because imagine sound traveling in a great sheet, in sort of a three-dimensional space. This is the power delivered per meter squared of a sound wave. We have half again. This is now the density of the air, or the water, or whatever it is. Again, the angular frequency, the amplitude squared, and the speed of the sound wave. For light, the equation looks very similar again, except now the density is replaced with epsilon naught, E is the electric field, and C is the speed of light. And this is power per meter squared as well. So you can see these three equations for the power look kind of similar. Just because the waves are in different media, the amplitude is different. Here it's a displacement, here it's a displacement, here it's an electric field. The speeds are different because they're different waves, and the constant, in this case, it's a linear density, a bulk density. In this case, it's this constant that comes from electromagnetism.